In this video, I want to show you how you basically can use methods known from natural sciences like physics or chemistry or biology in order to understand how a computer works and how to program this computer. Now, what you have here is the ABC Hello World program that you already typed in your editor, the so-called source code. Then you compiled it into an executable using the ABC compiler. And then you executed this program on your computer. And what we have here is basically the nature that you want to understand better, where you want to discover the laws of nature and explore them. And the source code is basically setting up an experiment. And when you run it on your computer, you do get some measurements. In this case, the output, for example, Hello World. Now, what we can do in order to do it like in natural sciences is making different experiments in order to understand better what the compiler is actually doing and what the computer is actually doing. A different experiment could be as simple as that, but maybe not for what I want to explain to you. Namely, I want to explain or prove by experiment that a program in ABC starts with function main, the so-called entry point of the program. Then it executes the statements between this curly parenthesis in this order and then leaves the program. Now, why is it not an ideal example for what I want to show you? It's not ruling out that the printfs are executed in this direction, in this order. For showing you this, a better experiment would be that, where I have different outputs. And then it's validating my hypothesis that the execution is starting here, doing the statements in this order, and then leaves the program. This is another experiment for exploring the control flow of a program. We have now two function definitions. One definition for function foo and one for function main. When you run this experiment on your computer, you see that as before, the execution begins with function main, although it's the second function in this program, the second function definition. So we again have here the entry point, then it's executing all the statements between the curly parentheses, and then it's leaving the program. Now the interesting thing is that when this first function call happens, the execution continues in this function foo. So it's jumping to function foo, executes all its statements, which is just one between the curly parentheses, and then it's resuming the execution again in function main after this function call. When the second function call happens here, then we again continue the execution here in function foo, execute all the statements, and then we resume the execution here. Now, why is it interesting? Somehow function foo knows where it should jump back into function main, where in function main the control flow should continue. And this will become more clear when we will do in another session some assembly programming where we have to do things more by ourselves and where we approach things bottom up. Then you need something like a stack in order to accomplish that. This is an experiment where we can learn a bit about how a compiler works, because we get here an error message. The compiler complains that foo is unknown. And this is kind of strange because as before, we have defined function foo here, so just at a different place. And the reason for this error message and what you can learn about how a compiler works from this example is that a compiler is reading a source file in a specific way. It's passing it from top to bottom. And that means at the time it's seeing this identifier foo, the compiler hasn't seen this part yet. So it's unknown to the compiler. So that's why the compiler doesn't know how to generate code for this function call. Now let's change this example a bit. With this modification, the program again compiles and you see the same output as before. I'm using this for introducing a new term and also telling you something about how a compiler is checking whether you correctly use functions that you defined. This is a so-called declaration of function foo. And you see the differences here, this semicolon at the end, compared to the definition of function foo. The declaration is simply telling the compiler how a function can be invoked. For example, in this case, it's telling the compiler that function foo does not expect any parameters and it doesn't return any value. And this means the compiler can check that this function call is correct. If you would try to call function foo with a parameter, for example with a 1, you will see this in the next example, the compiler would complain that you incorrectly use function foo. So basically a declaration is just giving the compiler some bookkeeping information about how to correctly use a function, whereas the definition is also a declaration. It also contains this information up here, but a bit more. It also tells the compiler how to generate code for the function itself. In this example, the definition of function foo was modified. Function foo now expects a parameter named val of type int. So you can speak out this colon as of type, and int is the type, int is short for integer. The function body is also modified. This function call for printf has now a different format string. We now have this placeholder %d, and this placeholder will be replaced with the value of val. And of course, we also see the declaration is different. The declaration now also specifies that function foo expects a parameter of type int. This val is optional, so check that out, that if you would remove that, you don't get an error message. The compiler still has the necessary bookkeeping information that foo expects a parameter of a certain type, and that's all that is needed for checking that the function call is correct. But if you would, for example, also skip this part here, the colon and int, then you would get an error message in the line where we call function foo with argument 1, too many arguments to function, even though we haven't modified the definition of the function foo down here. Now, of course, you also can play around with the function calls where we pass argument 1 and 2. You can use different values, but also check out what happens if you, for example, skip here the argument 1, if you leave it simply out. Then again, you get an error message because you incorrectly use function foo. In this case, because you have too few arguments that you pass to function foo. Of course, functions also can return a value, for example, an integer. And actually in this program, we are already using such a function printf. So far, I was using printf as if it was a built-in function, a function built into the language itself. But actually, that's not the case. Function printf is also declared, by the way, in this program, but the declaration is somehow hidden behind this so-called preprocessor directive. Now, there are several reasons why I didn't want to go into this detail, and I don't want to do this actually in this video, but I give you an idea that the nature is a bit more complex compared to what I showed you in the beginning. There's more involved than just the compiler and the computer. For example, also something like the preprocessor, which is essentially just including the content of a file, and relevant from this file is basically this line. Then there are also other things involved, for example, a linker, because in this program we don't have any definition for function printf. This code is actually never seen by the compiler. This code for printf will be linked to an object file after the compiler has generated some assembly code, but all these details are not so relevant right now. Also, for example, here the declaration of printf indicates that we have one parameter format or FMT for the format string of type pointer to character. And pointers is also something we will explore in more detail in another session. And then a second parameter, for example, here, this 3 dots indicates that this function printf has an arbitrary amount of additional optional parameters. So this is something you don't have to understand right now. It's not so relevant. It's also interesting why a function for printing out a string should return a value. And this is somehow indicating that, for example, an operating system might be required for printing some characters. And basically you invoke here a function which is interacting with the operating system and might fail. A printf might not be successful. In this case, printf returns 0, and otherwise, if it was successful, non-zero. So let's ignore these details for now, and let's look at an example where we actually have a function implemented by ourselves, which is returning some integer. And this is what you see in this example. So function foo is now the first function definition in this program, which is saving me some space on this slide. Function foo, as before, expects one parameter, val, of type int, and it now also returns value of type int. So again, the column can be spoken out loud as of type. So the return value is of type int. And here we have a return statement, which is also kind of new. And the return statement returns val times 2. In function main, you now see that printf has a format string with 2 placeholders. The first placeholder gets replaced with 1 in this case, and the second with the result of foo1. And then in the next call of printf, we have 2 and foo2. Now with functions that accept parameters and return values, we can make more interesting experiments. But for really interesting experiments, we at least also need control structures like if statements and loops. I will skip in this video things like local and global variables, but just to give you an idea how these control structures work, let's look at the next example. So the control structure, the if statement in this case, is here. You still have the control flow as before, that the function statements are executed in this order. But the if statement is a bit more complex. It's basically something that you can describe with a flowchart as follows. You have here this expression, val greater than 1, and such a conditional expression in this case usually gets in a flowchart described with this diamond. And here you have a condition which can be true or false. And if this condition is true, then the return statement here should be executed. So you can say you have here a branch true, and then you have here this return statement with val times 2, with this expression val times 2. And this is actually, in this case, then the point where the function returns and exits. So very simple. And otherwise, of course, if the condition is false, we branch to the return statement, in this case with 42 as expression. And then we also have here something interesting, that we have these 2 possible exit points. In this small modification, I'm avoiding the thing with 2 exit points in function foo. you see I now have just one return statement. The control flow is essentially always the same as before. We begin here when we call function foo, then we execute all its statements. In this case, we have two statements, the if statement and the return statement. And because we only have one return statement, we just have one exit point. What you also see here is that I do actually talk about variables, local variables in this video, because a function parameter is a local variable. You can change it. And I actually do this here and here with this expression statements. Here in the first expression statement in the then branch, I do overwrite val with the value of val multiplied by 2. And here with 42. So the flowchart in this case would look like that. First we check the condition, val greater 1. Then we have a true branch. In this val gets assigned the value of val times 2. And in the else branch, if the condition is false, val gets assigned the value 42. And after this, the branches are merged. And here we have our return statement. So, kind of simple, and this is how we can describe this control structures in general. And with another small modification, in particular here and here, we actually can turn this function foo into a function which is doing something more useful. In this case, it's computing the factorial of val recursively. Now, technically, the thing is very simple to understand, or it's basically the same as before. But you will see that sometimes to understand the logic behind this recursive function calls actually requires to understand how this so-called stack is used for function calls, and with this underlying concept and how it's technically realized. This is a story covered in dedicated extra sessions all over the semester. But back to an example where we actually do not do something useful, but where we can see how certain concepts are working. In this case, a while loop. Let me show you with a flowchart why this is called a while loop and why if statement is not a loop. The condition here is val smaller 10. And if this condition is true, then we go to this assignment where val gets tripled. And then we go back to check whether the condition is still true or not. Now, because we invoke the function only with positive numbers, sooner or later the condition will be false. And then we continue the execution of statements after the while loop with the return statement. And then we have reached the exit point. And it's called a loop because basically you see here this part where we loop back, and when you go back to the example with the if statement, you never have an arrow which is going back. And that's the difference. Now with this approach, learning by examples, by experiments, and most of all, learning by doing, you can come quite far. And you actually will. But sooner or later, you will appreciate a more formal description of certain things, like, for example, the syntax of the language. You want to know where do you have to use a semicolon, where do you have to use braces or parentheses, things like that. you not always just want to try out whether the compiler accepts your code or not. You also want to better understand the meaning of certain things. In the video so far, you saw, for example, that I gave a kind of description of the meaning of a function definition and the meaning of a declaration and where it is used. We will learn these things more and more over the semester by doing, for example, things, namely writing a simple compiler. And in some other lectures, we will also deal with things bottom up, where we approach things from the technical side, where we begin with logic gates and then step by step build some simple computer. And then in the end, basically things will converge, where you see that this bottom up and top down approach basically leads to something where you see the same thing from different angles and have a better understanding of things.